In this video, I'll be going over our notes for the properties of tangents. So two words that we're going to need to know today are a secant and a tangent, and we've already seen these two words, but a secant is just a line that intersects a circle in 2 points. So there's going to be 2 points where it touches, whereas a tangent is a line that's in the same plane as a circle that will intersect the circle in exactly 1 point. So we have seen both of these. One of the tricks to remember that would be secant kind of looks like the word second, so it touches the second time versus the tangent that only touches 1 time. So we're going to name all the parts from this diagram. If you think you can label them on your own, go ahead and pause the video and then press play when you're ready to review. We first have the segment HC, and we can see that that's going from a point on the circle to the center, which is just a radius. The segment BE is connecting 2 points on the circle, but it is not going through the center, so this is just a chord. The segment BH is connecting 2 points on the circle, but it is going through the center, so this is a diameter. The point E we can see is on the circle and it's intersecting with one line, so this is actually called the point of tangency. Now this isn't one we've technically defined, but it's just the point where a line and a circle intersect. When that line is a tangent, it is that point of tangency. So point E is where they're touching. Then the line DG, notice this has the 2 arrows on top of it. So DG, we can see that only touches the circle 1 time, so that's going to be a tangent line. Whereas the line BE, we can see it's touching the circle twice, which makes that a secant line. The point C is the center of our circle. And when we name a circle, we name it by its center. So we use this center circle symbol with the letter C to name the center of the circle, so it's called circle C. So next we're going to look at coplanar circles. And by coplanar, remember, it just means it's on the same plane. So 2 circles can intersect either in 2 points, 1 point, or at no points. So the coplanar circles that intersect in 1 point will be called tangent, but coplanar circles that have a common center are going to be called concentric. So I have an example of concentric circles here. We can see that they have the same center point. So each circle here has that same center. The blue circle is the smallest, the green circle is the largest, and they're all coming from that same center point. So we're going to look at how we can draw these tangents among these different circles. So if I were to try to connect a line, I want to draw the common tangents. I want to take a line and have it intersect each of my circles at just 1 point. So I'm going to move that over just a little bit. And notice we have to play around with it just to be careful to make sure that we're only intersecting once. And once I do that, I can see I have a point of tangency here and a point of tangency here. Well, I can do something very similar by creating a line the other way over here. And again, we're going to have to adjust that to make sure that it's only touching that circle once. And again, we have that point of tangency on this circle and on this circle. So what I just drew are called common internal tangents. And so it's a tangent to both circles because each of those lines is only touching each circle once, but they are common to the 2 circles, making them a common tangent. They're in between the 2 circles, making them internal tangents. Now we can also create a tangent that goes from here to here. Oops, I didn't create a line. By connecting these 2 circles. So notice I made this line, and I can also create a line down here that connects the 2 circles. So again, we have a common tangent because each of these tangent lines are touching the circle once. So this top line is touching this circle at 1 point and this circle at 1 point. The bottom line is touching each circle at 1 point only. So they're each creating, they're both tangents, but now we call them common external tangents. And that's because they're on the outside of those 2 circles. They're not in between there, so common internal tangents were the first 2. Common external tangents are what we call the second 2. So altogether, we were able to draw 4 separate tangents, 4 separate common tangents for these circles. Next, I can draw some more. I'm going to create my tangents on my next circle. I could draw very carefully a common internal tangent right here. And notice that that tangent, it has the same point of tangency for both circles. So that line is intersecting both of those circles where these circles themselves intersect. So it's still a tangent to both circles, but we can show that it's touching that one single point. So if I were to try to draw another tangent in between, it would still only touch at that one point there. Then I can create another tangent by connecting these, and I can do it again by connecting these ones. And again, we're going to have to play around with these a little bit to make sure that they look like they're exactly touching at one point only, to make sure that those are tangents. So we have a common internal tangent and two common external tangents here. We have these points of tangency that are showing up on each circle. So this one had 3 common tangents. Then our last set of circles, we can see that those circles are intersecting twice already. So we've already seen the circles that don't intersect at all, circles that intersect at one point, and now we have circles that are intersecting at 2 points. If we try to draw the tangents for these, we can't draw any common internal tangents. We are only able to draw common external tangents by drawing those on the outside of those circles. We aren't able to draw any internals because there would not be a point between them where it would only touch each circle once. Because if I try to draw a line here, similar to our last one, as soon as I try to start drawing this, I'm going to end up intersecting one of the 2 circles at least more than one time. So we're not able to draw that. So we can really only draw 2 common external tangents here. So now we have a theorem with our tangents. So in a plane, a line will be tangent to a circle if and only if that line is perpendicular to the radius of the circle at its endpoint on the circle. So what we mean by that is this tangent segment AC will be perpendicular to the radius right here if and only if it is a tangent. So it has to be a tangent, it has to be perpendicular. It's one of those if and only if statements. So if one part of that is true, the other part has to be true as well. And notice that we can see some other things starting to be marked there that we're going to look at a little closer as we continue studying tangents. So we are going to apply verifying that these line segments are actually tangents. Well, if we just said that to be a tangent, it has to be perpendicular, then we are trying to prove that this angle formed between the tangent and the radius must be a right angle. And in order to prove that, we're basically trying to prove, well, is this a right triangle? Because as we can see, we want this right angle. We have 2 potential legs here and a hypotenuse across from them. So we're going to use the Pythagorean Theorem to verify whether or not this is a right triangle, and therefore whether or not this is a tangent. So I'm going to take my 2 legs squared, take their sum, so 9 plus 16 should equal 25, and that is true, meaning yes, this is definitely a tangent because it was perpendicular to the radius. We check it again in the next one. We're trying to see are 3 and 9 forming that right angle. If they are, that means that a 3, 9, and 10 should fit into the Pythagorean theorem for us, so we're going to test it out. 9 plus 81 would make 90, not 100, and therefore this is not a right angle, so therefore 9 is not actually a tangent. Then we are going to check this next one. We can see that this 10 is the radius of our circle, meaning the diameter, or this entire leg of this right triangle that we want to be a right triangle, must be 20. So I'm going to take 20 and 48 as my 2 legs, square them and add them together, and see if they are equal to 52 squared. When I do that, I end up with 2,304 for 48 squared. Adding that together to make 2,704, which is the square of 52. So this one was true. Therefore, the first and last had a tangent, the middle did not, and we proved it using Pythagorean theorem. In our second set of applies here, we're looking to figure out what the length of R is, and we're told that B and S are points of tangency. So given that these are a point of tangency, we know that 80 must be a tangent, and therefore it is perpendicular to R. Same in our second one, we have point S, which is a point of tangency, meaning 24 is a tangent, so it is perpendicular to R. So we have two right triangles here, and we need to be able to figure out what r is. So we can use Pythagorean Theorem again to help us. It's just going to look a little bit different than what we've used before. I'm going to take r squared plus 80 squared, which are my two legs, and set that equal to my hypotenuse squared. Well, my hypotenuse is given to me in sections. I have 50 and I have r. So my entire hypotenuse is 50 plus r, and I need to square that entire binomial. This is something we haven't seen in a while, where when we are squaring an expression like this, we need to remember that we're really taking 50 plus r times 50 plus r like this. We can't just say 2500 plus r squared. We need to use the FOIL method, if you recall that from algebra. Remember, FOIL means first, outside, inside, last, and we need to make sure we're doing all of those steps to ensure we don't miss anything in our problem. So on the left side, we have r squared plus 6400 equals 50 plus r times 50 plus r. So I take my first, which is 50 times 50, so 2500, plus my outside, which is 50 times r, so 50r, plus my inside, r times 50, which is just another 50r, and my last, r times r, so r squared. I'm going to clean this up a little bit. I have 2500 plus 100r plus r squared. This is all equal to r squared plus 6400. So what I'm going to do is subtract r squared from both sides. When I do that, I'll just be left with this expression. I've gotten rid of r squared from each side, so now we can just subtract 2500. And when we do that, we're left with 3900 equals 100r. We'll divide each side by 100, so 39 will equal r. You can go back and check to make sure that this makes sense by saying, well, if these are both my radius, that makes my hypotenuse 89, so 80 squared plus 39 squared should be equal to 89 squared. And that's how you can double check that you solved this correctly to ensure that this is still a tangent and is mathematically correct there. So when we double check this, we do end up getting an expression that is true, or an equation that is true when we add these and check their squares. So this is correct. So try the second one on your own. Press play when you're ready to check. Again, we have a right triangle being formed where the leg is r and the other leg is 24. So r squared plus 24 squared is going to be set equal to our hypotenuse, which is r plus 18, and we're squaring it. That means we are multiplying a binomial, so we need to be careful and use FOIL here. So I'm going to take r plus 18 times the expression r plus 18. We're taking the first times the first, so r squared. The outside times the outside, so r times 18, which is 18r. Inside is 18 times r, so we have 18 plus r, 18 plus r, so 36r. And then our last is plus 18 times 18, which is 324. We set that equal to r squared plus 576. Again, our r squareds are going to cancel. If we subtract from each side, they'll go away. And we're going to subtract 324 from each side, leaving us with 252 equals 36r. We'll divide each side by 36, leaving us with 7 equals r. Double check yourself. Make sure that when you plug in 7 here, you get a right triangle that is true. So 7 squared plus 24 squared should equal 25 squared. So 49 plus 576 should equal 625, and that it does. So we know that we got our radius correct. Finally, we're looking at a theorem that states tangent segments coming from a common external point are always congruent. So in these diagrams, we have the point R that it has two segments that are coming off of it, RT and RS, and we can see that each of those are marked with a right angle, meaning that those segments are tangent to the circle. Since they're coming from the common endpoint R, that makes these two segments congruent. If they're congruent, we can set them equal to each other to solve for x. So I'm going to say that 3x minus 2 should equal 7. Add 2 to each side, 3x equals 9, so x should equal 3. Go ahead and pause the video and try the other two on your own. Here we can see that we have a point R that is coming from a common endpoint there, and we are going to say, well, those should be equal, so 28 equals 3x plus 4. And once we do that, we are going to subtract 4, divide by 3, so x should equal 8. And finally, we have 4x minus 9 should equal 15 because these two segments should be congruent to one another. we're going to add 9 from each side, or to each side. So 4x should equal 24. Dividing by 4 gets us x equals 6.